Hello friends, today we will continue with our next topic from slope deflection equation, that is sway type of portal frame. What is the meaning of sway type of portal frame? That when your portal frame, it is subjected to lateral displacements over there. That is, if I consider this example over here, a simple portal frame which is subjected to lateral loads over here. Lateral load means horizontal loads which are subjected to this rigid joint over here, and when this frame sways in this way, that is, if it's permit a horizontal displacement of amount delta, that type of frame we call it as a sway portal frame, and this delta, it is called as the sway coefficient over there. Okay, now the question is how these lateral loads occur over there. Okay, so these lateral loads occur due to earthquake or wind pressure at the portal frame, and your portal frame is subjected to lateral displacement over there. This frame sways in the direction of acting this load over there. That is the if this load is acting in right direction, your frame will sway in right direction, and if this load is acting towards left, your frame will sway towards left over there, and this is known as the concept of sway over there. Okay, basically these lateral loads, these are occurring due to two reasons over there. First is that is due to wind effect, and secondly that is due to earthquake effect over there. These are the two major reasons which leads to occurrence of this lateral loads over there. Okay, now if I consider any portal frame over there which is suppose 3 storer and 3 bays over there, which are having 3 stores and 3 bays, whatever this is called as the bay, and this is called as the story over there. That is, the vertically it will be called as story and horizontally it will be called as bay over there. Suppose this frame, it is subjected to lateral loads over there. I am marking these lateral loads over here. That is, suppose this is your load W1, this is your load W2, and this is your load W3 over there. So depending on this, the direction through which these loads are acting, that side it is called as the windward side. Okay, and the opposite side of that, it is called as the leeward side over there. Okay, so depending on this direction of these loads, these columns, is its CG is removed of this complete frame. Suppose its CG is acting at a distance x bar from this extreme left end over there. Okay, so depending on this CG, the columns towards the left hand side of this CG and columns towards the right hand side of this CG are subjected to tension and compression. So these columns will be subjected to tensile loads and these columns will be subjected to compressive loads over there. Now same in case of the single storage, whatever examples we are going to see under this, that will be only single storage and single bay examples over there. Okay, so that your analysis will be simple one. Now what are this horizontal displacement you are going to calculate over there, which due to this horizontal loads over there, these loads will be subjected at your rigid joints over, that is the joints meeting of beam and column. Okay, these loads occur due to the wind effect and due earthquake effect, and third criteria, this is again your geometrical properties of your frame over there. The geometrical properties of your frame, that is, if loads on this side, that is the windward side is different, and load on this leeward side is different, so your this loading, your geometrical properties get changed, and that leads to the sway displacement delta over there. Okay, so considering about the degree of kinematic indeterminacy for this. Okay, so whatever this frame is swaying over here, your normally the degree of kinematic indeterminacy, if I consider this example, frame A, B, C and D over there. Okay, so normally we calculate degree of kinematic indeterminacy for this such type of frame equal to 2. Those are your theta B and theta c over there. Okay, this is your non-sway frame. But if I apply a lateral load that is of amount P to this frame at joint B over there, okay, so what will happen? Due to this load P, this frame will be subjected to horizontal displacement over there of an amount delta. Okay, so in such case, so now this frame will be classified as your sway frame over there, sway portal frame. So in this case, your dk value comes equal to 3. Okay, how 3? That is, these two values will remain as it is, theta b and theta c, but here your one more value increases, that is your this sway coefficient delta and that acting direction of it. It will be treated as acting direction. Initially what we do, we consider theta b and theta c as clockwise in rotations, right? But this delta you have to consider according to the acting direction. Normally it is considered as towards the right always. Okay, so this is the difference between non-sway and sway frame, that your decay value, it increases by 1 over there. That is, what is this one? This is nothing but the amount of delta over there. So in this case, whatever we are calculating, the equilibrium equations over there. Okay, so in previous all the numericals I was telling you that your equilibrium conditions, what we are taking in our one step, equilibrium conditions we are taking. Okay, so I was saying you that your equilibrium conditions will be always equal to your value of dk. That is, if your dk value is 2, you will be having two conditions of equilibrium in your complete numerical order. But here that case gets changed over here. What happens if your this value increases by 1 in case of sway frames, but your this equation remains only 2 here? That is, if I consider example of this, if this is sway frame, its decay value comes equal to 3, but its equilibrium conditions will remain only equal to 2. That is, first condition will come at joint B and second condition will come at joint C over there. So we cannot find out 3 unknowns, that is theta B, theta C and delta, from these two conditions of equilibrium over there. So in that case, one more equation you need, and that equation will be your additional equation. We call it as shear equilibrium equation. We call that as shear equilibrium equation. Okay, so for calculating this shear equilibrium equation, we need to consider the equilibrium of these columns over there. That is, your this sway coefficient that normally affects to this column. Your beam member is not affected due to the sway. Okay, so normally you have to consider the equilibrium condition of only columns under this equation over there, considering the horizontal thrust acting at this support conditions over there. Suppose horizontal thrust is HA at your point A and horizontal thrust is HD at your point D. Okay, now we will see how the shear equilibrium is established over there. Okay, so firstly what I do, if I consider this this portal frame over there, I calculate the total summation of Fx equation for this. Okay, what Fx we do, we consider rightward forces as positive is equal to 0. Decay value for this is equal to 3 over there. That is, 3 are what? Theta B, theta C. Initially we assume it as clockwise, and 1 is your delta over there. Okay, so considering this Fx equation, what equation we get here? That is, HA plus HD plus P will be equal to 0. So horizontal forces we have considered HA plus HD plus P is equal to 0. So if I want to calculate this shear equilibrium equation, I have to calculate the values of this horizontal thrust acting at point A and D. Okay, so for calculating this, I consider the equilibrium of columns over there. So suppose this is my column number 1, that is your column A, B. Okay, now whatever this equilibrium you consider, you have to keep the loadings as it is on this, only span loadings. You have to keep the span loadings on it. Suppose a UDL is acting on this span over there, so that loading you have to keep as it is on this. Okay, if point load is acting on this column AB, between this span you have to keep that as it is over here. Okay, so what I am doing, I am keeping this horizontal thrust HA as over here. Okay, and I am applying here moments, that is MBA and MAB at both of these joints over there. These are my final moments occurring at point A and occurring at point B for AB column. Okay, so initially one more thing what you have to do, while assuming these moments, always assume those in clockwise direction. Don't assume one clockwise and one anti-clockwise, so that will increase your confusion over there. So what you do, you assume both of these moments acting directly in clockwise direction. Suppose length of this column is your L1. Okay, so what I do, I have to calculate the value of HA. So what I'll do, I'll take the moment at point B. So I'm writing here equation summation of moment at B is equal to 0, treating clockwise moments again by positive. Okay, so what equations you will get here? Firstly, moment occurring at point A, MAB, plus moment occurring at point B, MBA. Both are clockwise, and clockwise we consider positive, so both are positive over here. And this moment of HA along this point B, that will be HA into L1, and that moment comes anti-clockwise in nature, so I treat as negative is equal to 0. So if I calculate value of HA over there, I'll get that equal to MAB plus MBA divided by L1. Okay, so MAB and MBA values you will be getting from your initial steps, that is from slope deflection equation. That values you will substitute here, you will get the final value of HA over there. Okay, now same way what I'll do, and what you do, you substitute this value of HA in your this Fx equation. Okay, nextly what I do, I consider this second equilibrium of column, that is column CD over there. Okay, so this is my joint C, this will be my joint D. Again horizontal thrust is acting at point D, that is your HD. Okay, suppose length of this column is your again H2. Moment acting here will be MCD, moment acting here will be your MDC. Okay, again I am telling you, initially while assuming these moments, you have to consider this moment always in a clockwise direction. So I have to calculate the value of HD. So again I'll consider the moment at point C is equal to 0, treating clockwise moments as positive. So what equation I get from here, that is MCD plus MDC minus HD into L2 is equal to 0. Okay, so if I simplify this, for the value of HD, I'll get as HD is equal to MCD plus MDC divided by L2. So this will be, suppose this is my equation number A, this will be my equation number B, equation number C. I'll substitute equation B and C in your equation number A over there. So total final equation for shear equilibrium equation I'll get as MAB plus MBA divided by L1 plus next is your HD value, that is MCD plus MDC divided by L2 plus what are horizontal loads given to you in your numerical is equal to 0. So this final equation, that will be called as your shear equilibrium equation over there. Okay, so this equation you have to plot in your this sway frame over there, that is conditions of equilibrium will be equal to 2, that is 2 equations you will get from here, and one more equation you will be needing, that we will get from your shear equilibrium equation. So now it will be feasible, that is 2 plus 1, that is you will get equal to 3 equations, and your unknowns are now 3. So that will be easy for you to calculate these 3 numbers of unknowns. You solve these 3 equations simultaneously, you will get the values of unknowns over here, and simply you substitute these values in your slope deflection equation, and you will get the final moments over there. Okay, very simple it is. So don't get confused, only just what you have to remember, that if your frame is sway frame, you have to consider your decay value equal to 1. Sway frame is what? It is the frame which sways to the lateral displacement due to the lateral loads over there. Okay, so now we'll see for the numericals in your this sway type of portal frames over there. Okay, thank you so much.